Right now, somewhere in the direction of the constellation Virgo, a galaxy is sitting in the darkness. It has been sitting there for billions of years, utterly indifferent to whether anyone knows it exists. It contains 100 trillion stars. Its diameter stretches across 4 to 6 million light-years of space, and the light you would need to see it left that galaxy over 1 billion years ago, before complex animal life had ever drawn a single breath on this planet. 100 trillion stars. That number will mean nothing to you right now. That is not your failure. That is simply what happens when the human brain encounters quantities it was never designed to process. But by the time this journey is over, you will have felt the weight of that number in a way that no statistic alone could ever produce. You will understand, not just intellectually, but somewhere deeper, what it means for a single structure in the universe to be that large. But here is what most people get wrong when they first hear about this galaxy. They assume the shock ends with the size. They assume that once you have heard the number, once you have nodded at the figure of 4 to 6 million light-years, you have understood what you are dealing with. You have not. The size is only the beginning. What lies beneath that number, the history that produced it, the physics that governs it, the future that awaits it, is far stranger and far more devastating to your sense of scale than any single measurement could convey. The galaxy is called IC 1101, and it is the largest galaxy humanity has ever found. If you find yourself drawn to questions that have no comfortable answers, to journeys that leave the universe feeling simultaneously more beautiful and more incomprehensible than it did before, then do me a small favor and hit that like button and subscribe to this channel. It genuinely helps this channel reach more people who want to keep exploring the cosmos together. Now make yourself comfortable. Clear your mind of everything that feels urgent and small, because we are about to travel a very long way. Let's begin. Before we can understand what IC 1101 is, you need to understand where you are standing. You need a reference point. Without one, the numbers we are about to discuss will wash over you like water over stone, leaving no impression at all. So let us start here. Let us start with home. You live on a planet called Earth. That planet orbits a star called the Sunday. The Sun is, by most meaningful measures, an unremarkable star. It is not particularly large, it is not particularly bright, it is not young, and it is not ancient. It sits roughly in the middle of the stellar population in terms of size and temperature and luminosity. There are stars in the universe 1,000 times larger. There are stars 1,000 times smaller. Our Sun is simply one of the vast majority, a medium star burning hydrogen into helium in a quiet, stable way, producing just enough light and heat to make life possible on one small rocky world circling it at just the right distance. The Sun sits approximately 26,000 light-years from the center of our galaxy, the Milky Way. That distance, 26,000 light-years, is already almost impossible to feel. A light-year is the distance light travels in a single year, and light travels at roughly 6 trillion miles per year. So 26,000 light-years is approximately 156 quadrillion miles. The number becomes meaningless almost immediately. So let us try something else. If you could somehow board a spacecraft and travel at the speed of light, the fastest speed anything in the universe is permitted to travel, it would take you 26,000 years to reach the center of your own galaxy from where you are right now. Not 26,000 hours, not 26,000 days, 26,000 years. That is longer than the entire recorded history of human civilization. It is longer than the time since the last ice age ended and humans first began building permanent settlements. You could watch every empire in human history rise and crumble and still not arrive. And that is just the distance to the center of our galaxy, not to the edge. The Milky Way stretches approximately 100,000 light-years from one side to the other. Our solar system sits somewhere between the center and the outer rim, tucked into a relatively quiet region called the Orion Arm. If you wanted to cross our galaxy from one edge to the other, traveling at the speed of light without stopping, it would take you 100,000 years. 100,000 years is longer than our species has existed in its modern form. Every cave painting, Every language, every war, every city, every act of love or cruelty or genius in the entire span of human existence fits inside a fraction of the time it would take to cross our own galaxy. The Milky Way contains somewhere between 200 billion and 400 billion stars. Each of those stars is a sun. Each one is a nuclear furnace, fusing hydrogen atoms into helium, releasing energy in the process, radiating that energy outward as light and heat into the surrounding darkness. Some of those stars are larger than our Sunday, many are smaller. Some burn blue and ferocious and die in millions of years. Others burn red and dim and will outlive the current age of the universe many times over. Our sun is expected to keep burning for another 5 billion years. That itself is a span of time so vast as to be functionally incomprehensible to a creature that lives for less than a century. The nearest star to our sun is a small red dwarf called Proxima Centauri. It sits approximately 4¼ light years away. In terms of the Milky Way's total diameter, that is an almost laughably small distance. It is less than 1/10,000th of the width of our galaxy, and yet reaching Proxima Centauri would be an almost impossible task with our current technology. NASA's Voyager 1 spacecraft, launched in 1977, is the fastest human-made object ever to leave our solar system. It is traveling at approximately 38,000 miles per hour relative to the Sunday. At that speed, Voyager 1 would take roughly 73,000 years to reach Proxima Centauri. 73,000 years to reach the nearest star. The space between stars is not simply empty. The word empty does not do it justice. It is an absence so total, so absolute, so devoid of anything at all that no human environment can approximate it. If you shrank the sun down to the size of a single grain of sand and placed it on a table in front of you, Proxima Centauri would be another grain of sand sitting approximately 4 miles away. The space between those two grains would contain essentially nothing. A few stray atoms, an occasional particle of radiation, the faint whisper of magnetic fields stretching between stellar bodies. But for all practical purposes, nothing. This is the texture of our galaxy. Not a dense cloud of closely packed stars, but an almost unimaginable emptiness punctuated at vast intervals by isolated fires. And yet, when you step back far enough, when you look at the Milky Way from a distance of several million light years, all of that emptiness disappears into the aggregate glow of hundreds of billions of stars. The galaxy becomes a thing of breathtaking beauty, a flat rotating disk with curving spiral arms trailing outward from a bright central bulge, like a pinwheel of light spinning slowly in the dark. The spiral arms are regions of higher star density, places where gas and dust have been compressed by gravitational waves moving through the disk, triggering the birth of new stars. The Milky Way is not a static structure. It is alive with the constant cycle of stellar birth and death. New suns igniting in clouds of collapsing gas, even as old ones burn out and leave behind white dwarfs or neutron stars or black holes. Our solar system orbits the center of the Milky Way at a speed of approximately 500,000 miles per hour. Even at that tremendous velocity, it takes our solar system about 250 million years to complete a single lap around the galactic center. Astronomers call this period a cosmic year or a galactic year. The last time our solar system was in roughly its current position relative to the galactic center, the most complex life on Earth was simple marine organisms. The dinosaurs had not yet appeared. The continents looked nothing like they do today. 250 million years of planetary history compressed into a single orbit. This is our home, 100,000 light years across, 200 to 400 billion stars, a single orbit taking 250 million years. It is enormous beyond easy comprehension, and IC 1101 makes our entire galaxy look like a speck of dust floating in an empty room. The Milky Way is not alone in space. No galaxy is. Galaxies exist in gravitational communities called groups and clusters, bound together by their mutual gravitational attraction, orbiting around shared centers of mass over billions of years. Our Milky Way belongs to a small community called the Local Group, which contains about 80 known galaxies. Most of them are dwarf galaxies, small, irregular collections of a few billion stars orbiting as satellites around the two dominant members of our group. Those two dominant members are our Milky Way and the Andromeda Galaxy. Andromeda sits approximately 2.5 million light-years from us. On a clear autumn night in the northern hemisphere, you can actually see it with the naked eye. It appears as a faint, slightly elongated smudge of light near the constellation Andromeda, so dim that most people mistake it for a star or miss it entirely. But what you are actually seeing, if you know where to look and the sky is dark enough, is the combined light of approximately 1 trillion stars, the most distant object visible to the unaided human eye. Andromeda is somewhat larger than our Milky Way. Its stellar disk stretches roughly 220,000 light-years across, about twice our diameter. It contains perhaps 2 to 3 times as many stars. By most conventional measures, Andromeda is a large, impressive galaxy. But even Andromeda, the largest member of our local group, even this galaxy containing 1 trillion stars spread across 220,000 light-years of space, would fit inside IC 1000, 101 with room to spare. Not as a tight fit, not barely. IC 1000, 101 would swallow Andromeda and barely register the addition. The local group itself, all 80 of its galaxies, including both the Milky Way and Andromeda, and every dwarf satellite orbiting either of them, the entire gravitational community we call home, would fit inside IC 1000, 101 with room remaining. That is the creature we are about to examine. The night of June 19th, 1790, was not a night that anyone recorded as particularly significant. There was no ceremony, no anticipation, no sense that something historic was about to happen. A man simply pointed a telescope at the sky, as he had done thousands of times before, and wrote down what he saw. That man was William Herschel. He was 51 years old, a German-born astronomer who had emigrated to England and built himself a reputation as one of the most meticulous observers of the heavens the world had ever produced. 9 years earlier, in 1781, he had discovered the planet Uranus, the first new planet to be found in recorded history. Using a telescope he had built himself in his back garden in Bath. The discovery had made him famous. King George III had appointed him court astronomer and provided him with a salary and a residence near Windsor Castle. In return, Herschel was expected to show the royal family interesting things through his telescopes and continue his systematic surveys of the sky. By 1790, Herschel was working with what was then the largest telescope in the world, a reflector with a mirror 48 inches across, a massive iron tube 18 inches in diameter, mounted in the garden of his home in Slough. Operating this instrument was not a simple matter. The telescope was so large that Herschel could not look through it while standing on the ground. He had to be hoisted up in a kind of wooden scaffold, calling observations down to his sister Caroline, who sat below in the cold with a notebook and a candle, recording every word her brother spoke into the darkness above her. On that June night, Herschel swept his telescope through a region of sky in the direction of the constellation Virgo. He was systematically cataloguing celestial objects, a project he had been engaged in for years, and he had already documented thousands of what he called nebulae, cloudy patches of light that refused to resolve into individual stars no matter how powerful the telescope. Some of these nebulae were clouds of gas within our own galaxy, places where stars were being born or where they had died. Others were something else entirely, though Herschel had no way of knowing that yet. He noticed a faint smudge of light, slightly brighter at its center than at its edges, oval in shape. He described it carefully in his notes, recorded its position in the sky, and moved on to the next object. The observation took perhaps a few minutes. Then the night continued, and he swept on to hundreds of other objects before dawn forced him inside. He had just seen IC 1000, 101 for the first time in human history. He had no idea what he was looking at. For more than a century after Herschel's observation, that faint smudge remained exactly what it appeared to be, a mystery. It was catalogued eventually as part of a systematic index of celestial objects, compiled in the late 19th century. That catalogue, gave it the designation IC 1101, the IC standing for Index Catalog, a dry bureaucratic label for something that would one day be recognized as among the most staggering objects in the observable universe. But in the decades following its discovery, it sat quietly in reference books, alongside thousands of other nebulae. Just another entry in a long list of things astronomers had noticed and not yet understood. The problem was not a lack of curiosity. The problem was a lack of tools. To understand what IC 1101 truly was, astronomers needed to know how far away it was, and measuring cosmic distances at the scale required was something humanity simply did not yet know how to do. Everything changed in the 1920s, and it changed because of a single man working with a single telescope in the mountains above Los Angeles. Edwin Hubble was 35 years old in 1924 when he made the discovery that would permanently alter our understanding of the cosmos. He was working at the Mount Wilson Observatory in California, using what was then the most powerful telescope on Earth, a reflector with a mirror 100 inches across. He had been observing a fuzzy patch of light called the Andromeda Nebula, which most astronomers of the time believed to be a cloud of gas within our own galaxy, perhaps a region where new stars were forming. Hubble was looking for a specific type of star called a Cepheid variable. These stars pulsate. They brighten and dim in a regular, predictable rhythm, and the period of that rhythm is directly related to how intrinsically luminous the star actually is. A Cepheid that completes one pulsation cycle every 10 days is inherently brighter than one that completes a cycle every 5 days. This relationship, discovered by astronomer Henrietta Swan Leavitt in 1908, while she was working as a human computer at the Harvard College Observatory, meant that Cepheids could serve as what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears, the difference tells you how far away it must be. Hubble found Cepheid variables in the Andromeda Nebula. He measured their pulsation periods, he calculated their intrinsic luminosities, and then he calculated how far away they had to be to appear as faint as they did from Earth. The answer stopped him cold. The Andromeda Nebula was not within our galaxy. It was not a nearby cloud of gas. It was approximately 1 million light-years away, far beyond even the outermost edges of the Milky Way. It was an entirely separate galaxy, an island universe of billions of stars, existing entirely independently of our own. We now know Hubble's original distance estimate was off by about a factor of 2. Andromeda is actually closer to 2.5 million light-years away, not 1 million. But the fundamental conclusion was correct, and it was devastating to every assumption humanity had ever made about the scale of existence. The Milky Way was not the universe. It was not even a significant fraction of the universe. It was one galaxy among what would turn out to be an almost incomprehensible number of galaxies, stretching outward in every direction to distances that made the mind go quiet and still. The universe was not a room. It was not a building. It was not even a city. It was something for which no human metaphor had ever been constructed, because nothing in human experience had ever required such a metaphor before. Once Hubble's discovery reshaped the scientific consensus, astronomers began to look at all those mysterious nebulae with new eyes. What had appeared to be clouds within our galaxy were, in many cases, entirely separate galaxies, each containing billions of stars, each sitting at distances that made the mind retreat from the attempt to comprehend them. The catalogue of the universe expanded overnight from one galaxy to countless billions, and among those newly understood objects was a faint oval smudge, first recorded by William Herschel on a June night in 1790. As the decades passed and telescopes grew more powerful, astronomers began to realize that IC 1101 was not merely another galaxy. It was something different in degree, so extreme that it began to seem different in kind. Every measurement pushed its dimensions further than expected. Every new observation suggested a scale that strained credibility. IC 1101 sits approximately 1,070,000,000 light-years from Earth, in the direction of the constellation Virgo. It resides at the center of a galaxy cluster called Abell 2029, a dense gravitational community of hundreds of galaxies all bound together and orbiting around a common center of mass. And at the heart of that cluster, dominating everything around it with the quiet authority of sheer mass, sits IC 1101. The numbers, when you first encounter them, do not feel real. The diameter of IC 1101 is estimated at somewhere between 4 and 6 million light-years. Our Milky Way, which already seemed so vast as to be beyond true comprehension, is 100,000 light-years across. IC 1101 is therefore somewhere between 40 and 60 times wider than our entire home galaxy. If you placed IC 1101 where the Milky Way currently sits, its outer edges would extend millions of light-years in every direction. The Andromeda Galaxy, currently 2.5 million light-years away from us, would find itself well inside the body of IC 1101. The Triangulum Galaxy, another member of our local group, would be consumed. Every dwarf galaxy currently orbiting the Milky Way as a satellite, the Large Magellanic Cloud, the Small Magellanic Cloud, the dozens of smaller companions whose names are known only to specialists, all of them would simply become tiny components of IC 1101's vast stellar body. Our entire local group, every galaxy we have ever considered our gravitational neighborhood, would fit inside this single structure. And the stars, 100 trillion stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. Let us be generous and say 400 billion. IC 1101, with its 100 trillion stars, contains roughly 250 times more stars than our home galaxy. If every star in the Milky Way were a single grain of sand, you would have a small beach. IC 1101 would be a desert stretching further than you could walk in a lifetime. If you attempted to count the stars in IC 1101 at a rate of 1 per second, never sleeping, never pausing, never stopping for any reason whatsoever, it would take you approximately 3,170,000 years to finish counting. If you had begun counting at the moment the first anatomically modern humans appeared on Earth, you would not yet be halfway done. You would still have millions of years of counting ahead of you. Your species would have risen, thrived, changed beyond recognition, and possibly vanished before the last star was tallied. 100 trillion. Let that number sit with you for a moment before we continue. The light we see from IC 1101 today is ancient beyond easy description. It left that galaxy when Earth was a very different world. More than 1 billion years ago, when the photons now reaching our telescopes first began their journey, the most complex life on this planet was in the early stages of what biologists call the Ediacaran period. Soft-bodied creatures, strange and alien by any modern standard, drifting through shallow seas. Nothing that would be recognizable as a fish, let alone an animal with a spine, let alone a creature capable of looking up at the night sky and wondering what it saw. Every major event in the history of life on Earth happened while the light now illuminating our images of IC 1101 was crossing the void between galaxies. The Cambrian explosion, when the fundamental body plans of all modern animals first appeared, the emergence of the first fish, the first land plants, the first insects, the rise of the dinosaurs, their dominance for 160 million years, their extinction, the first mammals, the first primates, the first hominids, the entire evolutionary history of the human lineage, from our earliest ape-like ancestors through every stage of human development to the moment you are experiencing right now. All of it happened while this light was traveling, and it is only now, at this moment, arriving at the mirrors of our telescopes. What does that mean? It means that what we see when we observe IC 1101 is not IC 1101 as it exists today. We are looking at a fossil, a photograph taken by the universe itself over 1 billion years ago and delivered to us only now. The IC 1101 that exists at this precise moment in cosmic time is completely unknown to us. The information about its current state is still in transit, traveling toward us at the speed of light, and will not arrive for another billion years. We are, in the deepest sense, archaeologists of the cosmos. And what we have excavated, what those ancient photons have revealed to us across more than 1 billion years of travel, is a structure so immense that every prior notion of galactic scale has to be quietly set aside and replaced with something far more unsettling. This is what William Herschel saw as a faint smudge in his eyepiece on a June night in 1790. This is what Edwin Hubble's generation of astronomers began to comprehend when they first understood that the universe contained not one galaxy but billions. This is what the Hubble Space Telescope has imaged in stunning detail, what X-ray observatories have mapped in the hot gas surrounding it, what radio telescopes have detected emanating from the violent activity at its heart. One galaxy, 4 to 6 million light-years across, 100 trillion stars, 1 billion light-years away. The largest galaxy humanity has ever found, but we have only just arrived at its doorstep. We have not yet looked inside. There is a question that follows naturally from everything we have just established. If IC 1101 is 40 to 60 times wider than the Milky Way and contains 250 times more stars, then how did it get that way? What process, operating over what span of time, could produce something so far outside the ordinary range of galactic scale? The answer is not gentle. It is not the result of a galaxy simply being born large, of some primordial cloud of gas collapsing into a structure of exceptional size in a single act of cosmic formation. The answer is older than that, and darker. IC 1101 grew to its current dimensions through an act of sustained violence that has been repeating itself for billions of years, across distances that dwarf anything in human experience, consuming victims one after another in a process that astronomers, with a precision that borders on understatement, call galactic cannibalism. IC 1101 has been eating other galaxies, not metaphorically, not in some abstract, gravitational sense, literally consuming them, pulling them apart with tidal forces, stripping away their stars and gas, absorbing all of that material into its own growing body. Astronomers estimate that IC 1101 has undergone at least 76 major mergers over the course of its long history. 76 separate occasions on which a substantial galaxy, something containing billions or tens of billions of stars, fell into IC 1101's gravitational grip and was ultimately destroyed and absorbed. And those are only the major mergers. The minor ones, the dwarf galaxies and small irregular collections of stars that were consumed without leaving significant traces in the data, number far higher. To understand how this works, you need to understand how gravity operates at the scale of galaxies. And to understand that, it helps to begin with something more familiar. Imagine two massive objects moving through space. They do not need to be heading directly toward each other. They simply need to pass close enough that each one feels the gravitational pull of the other. When that happens, something subtle begins to occur. Each object's path bends slightly toward the other. Their trajectories curve. If they are moving fast enough, they might swing past each other and continue on their separate ways, their paths altered, but their separation maintained. But if they are not moving fast enough, if the gravitational attraction between them is sufficient to overcome their relative velocities, then something else happens entirely. They become bound to each other. Not immediately, not in any dramatic sudden fashion, but gradually, over time spans measured in hundreds of millions of years, they begin to orbit around their shared center of mass. And as they orbit, various forces act to drain energy from the system. The gravitational interaction of each galaxy with the stars inside the other, what physicists call dynamical friction, slows them down. Their orbits decay. They swing past each other again and again, each pass bringing them closer, each close approach distorting their shapes more severely, until finally the distinction between two separate galaxies ceases to have any meaning. They have merged. But the process is not quiet, and it is not clean. When two galaxies undergo a close encounter, The gravitational forces involved are not uniform across the extent of either galaxy. The near side of each galaxy feels a stronger pull than the far side. This difference in force, called a tidal force, stretches and distorts the galaxies in dramatic ways. Stars get pulled out of their normal orbits. Long streams of stellar material, which astronomers call tidal tails, are drawn out from each galaxy like streamers trailing behind them through space. These tidal tails can extend for hundreds of thousands of light years, ghostly ribbons of stars marking the violence of the gravitational encounter. If you could watch a galactic merger compressed into a few minutes, the way certain computer simulations allow, what you would see would be extraordinary. Two galaxies, each with their own structure and identity, approaching each other like slow-motion storms. Their outer edges begin to distort as the tidal forces grow stronger. Long arcs of stars are pulled loose and flung into intergalactic space. The galaxies swing past each other, separate briefly, then turn and fall back toward each other on a second pass. With each subsequent close approach, they lose more energy to dynamical friction. Their separation grows smaller, their structures become more entangled. Finally, in a collision that takes hundreds of millions of years and yet is still, by cosmic standards, relatively swift, the two galaxies merge into one. What emerges from this process is something fundamentally different from either of the original galaxies. The orderly rotating structures that characterize spiral galaxies, the flat disks, the curving arms, the organized patterns of stellar motion, are destroyed by the chaos of the merger. Stars that were once moving in neat circular orbits around a galactic center are now moving in complex, overlapping trajectories that point in every direction. The result, once the system has had time to settle, is what astronomers call an elliptical galaxy, a smooth, roughly oval-shaped structure with no spiral arms, no flat disk, no obvious internal organization, just a dense concentration of stars gradually thinning toward the edges, like a softly glowing egg floating in the dark. This is what IC 1101 is, an elliptical galaxy, and the fact that it is an elliptical galaxy tells you, immediately and unambiguously, that it has experienced so many mergers that any original structure it might once have possessed has been completely and irreversibly erased. The evidence for IC 1101's cannibalistic history is not hidden. It is written directly into the galaxy's structure, visible to any astronomer who knows how to read it. When astronomers study the stellar populations within IC 1101, they find something revealing. Not all the stars are the same age. Not all of them have the same chemical composition. In a galaxy that had formed in a single event from a single cloud of gas, you would expect to find stars of broadly similar ages and similar elemental makeup, the variations arising from the normal processes of stellar evolution over time. But what astronomers find in IC 1101 is different. There are populations of stars with distinctly different ages, as if multiple generations of star formation happened at different times. There are stars with chemical signatures that suggest they formed in entirely different galactic environments before being absorbed into IC 1101's body. These different stellar populations are like geological layers in ancient rock. Each one records a different chapter of the galaxy's violent history. The oldest stars, ancient red and yellow objects burning slowly through their remaining fuel, are likely survivors of the original galaxy that seeded IC 1101's growth billions of years ago. Younger populations record the starbursts that accompanied major mergers, the brief, explosive episodes of star formation triggered when merging galaxies compressed their gas clouds and ignited new stellar nurseries by the billions, and the chemically distinct populations, the stars with elemental fingerprints that do not match the rest, are foreigners. Stars born in galaxies that no longer exist, now absorbed so completely into IC 1101 that only their chemical signatures betray their origin. 76 major mergers, each one a galaxy that once existed as an independent structure, with its own history, its own stellar populations, its own central black hole, all of them now dissolved into the body of this enormous elliptical, their identities erased, their stars scattered into new orbits, their mass added to IC 1101's relentless accumulation. The core of IC 1101 also carries the marks of this violent history. A study conducted in 2017 using images from the Hubble Space Telescope measured IC 1101's central region and found that it stretches across nearly 14,000 light-years. Just the core, not the full extent of the galaxy, but merely its innermost region. 14,000 light-years is larger than many entire dwarf galaxies. The core of IC 1101 alone contains more stars than most galaxies in the observable universe. But this core, enormous as it is also unusually faint for its size. There are fewer stars in the very center than theoretical models would predict for a structure of this mass, and astronomers believe they understand why. The repeated mergers of supermassive black holes at IC 1101's center, which we will examine in detail in the next part of this journey, have in each instance flung enormous numbers of stars outward from the very heart of the galaxy through a process called gravitational scouring. Each time two black holes merged at the center of IC 1101, their interaction with surrounding stars sent those stars flying outward at tremendous velocities. Estimates suggest that hundreds of billions of solar masses worth of stars may have been scattered from IC 1101's core over the course of its history. More stellar material than exists in many entire galaxies, flung outward by the violence of black hole mergers deep inside this cosmic giant. The result is a core that is enormous in physical extent, but paradoxically depleted at its very center. A vast emptiness at the heart of the largest galaxy ever found, carved out by billions of years of gravitational violence that most structures in the universe never experience even once. And now we arrive at what may be the most striking paradox of IC 1101. This galaxy, with its 100 trillion stars, with its 4 to 6 million light-year diameter, with its 76 major mergers, and its long history of consuming everything within its gravitational reach, is dying. Not dying in the immediate sense, not collapsing or exploding or fading visibly on any timescale a human civilization could observe, but dying in the sense that matters most on cosmic scales. IC 1101 is no longer making new stars. The furnaces are going out, one by one, and nothing is being built to replace them. To understand why, you need to understand what stars are made of and where that material comes from. Stars form from clouds of gas, primarily hydrogen, the simplest and most abundant element in the universe. When a region of a gas cloud becomes dense enough, gravity takes over, pulling the gas together until the pressure and temperature at the center reach the threshold for nuclear fusion. Hydrogen nuclei begin fusing into helium, releasing energy in the process, and a new star ignites. For this process to happen, you need gas. Cold, dense gas, gathered in sufficient quantities to collapse under its own weight. IC 1101 has run out of that gas. The mechanism by which this happened is directly connected to the same mergers that made IC 1101 so large. Each time IC 1101 consumed another galaxy, it also consumed that galaxy's gas supply. Some of that gas was compressed so rapidly by the gravitational violence of the merger that it ignited in a starburst, forming billions of new stars in a brief, intense episode of stellar creation before the fuel was exhausted. Some of it was heated to such extreme temperatures by the energy released during the merger that it expanded and escaped the galaxy entirely, blown out into the surrounding intergalactic medium. Some of it fell toward the central black hole, where it was consumed or converted into energy and ejected. Either way, the gas was gone. Over billions of years and dozens of major mergers, IC 1101 converted most of its available raw material into stars, scattered it into space, or fed it to its central black hole. What remains today is a galaxy that has essentially used up its fuel. The stars that exist now will continue to burn for billions of years to come, some of them for trillions of years. But as they eventually exhaust their fuel and die, there will be no new generations to replace them. No stellar nurseries are igniting in IC 1101's body. No new suns are being born in clouds of collapsing gas. The 100 trillion stars that shine there today are, in a very real sense, all that IC 1101 will ever have. They are its last generation. Imagine a civilization that has conquered every nation on Earth, accumulated all the resources the planet has to offer, grown to the maximum size that its world can support. And then imagine that civilization discovering it can no longer have children. It still stands. It is still powerful beyond anything that came before it, but it has reached its limit. It will not grow further. It will only, very slowly, very quietly, begin to diminish. That is IC 1101, the largest, most dominant galaxy in its cluster, the product of billions of years of cosmic conquest. And at the peak of its accumulated power, quietly, without drama, beginning its long, slow fade into the dark. The stars burning in IC 1101 right now are the last light this galaxy will ever produce. The universe will not see a galaxy like this grow larger. There are no more victims close enough to consume, no more gas reserves to ignite, no more mergers on the horizon significant enough to change IC 1101's trajectory. What has been built over billions of years of violence and accumulation has now reached its final form. 100 trillion stars, burning in a dying giant, sending their light outward in every direction, including toward a small rocky planet more than 1 billion light-years away, where creatures who live for less than a century have somehow found a way to look back across that impossible distance and understand what they are seeing. But before we follow IC 1101 into its long future, we need to look at what sits at its center, because the heart of this galaxy contains something that makes everything we have discussed so far seem, by comparison, almost restrained. At the center of every large galaxy in the observable universe, there is a black hole. This is not a hypothesis. It is not a theoretical prediction awaiting confirmation. It is one of the most thoroughly established facts in modern astrophysics, supported by decades of observation across every wavelength of light our instruments can detect. Wherever astronomers have looked, in spiral galaxies and elliptical galaxies, in active galaxies blazing with violent energy, and in quiet ones like our own Milky Way, at the center of every substantial galactic structure they have examined, a supermassive black hole waits. Our own Milky Way has one. It is called Sagittarius A star, named for its position in the direction of the constellation Sagittarius, as seen from Earth. Sagittarius A star contains approximately 4 million times the mass of our Sun, compressed into a region of space smaller than the distance between our Sun and the nearest star. 4 million solar masses sounds enormous. In the context of a single star or a planetary system, it is inconceivable. But in the context of what we are about to discuss, 4 million solar masses is almost nothing. The Andromeda Galaxy, our nearest large neighbor, has a supermassive black hole at its center, containing somewhere between 100 million and 200 million solar masses, roughly 50 times more massive than the black hole at the center of our Milky Way. Already, the numbers are beginning to climb toward regions that resist comprehension. Now consider what sits at the center of IC 1101. Astronomers estimate that the supermassive black hole at IC 1101's core contains somewhere between 40 billion and 100 billion times the mass of our Sunday. Let us take the middle of that range and call it 50 billion solar masses, understanding that this figure carries significant uncertainty because measuring black hole masses at such distances involves layers of assumption and inference that introduce unavoidable error. Even with that uncertainty, the number is staggering: 50 billion solar masses. The black hole at the center of IC 1101 is approximately 12,500 times more massive than the black hole at the center of our entire Milky Way. Our galaxy's central black hole, 4 million solar masses, sits inside IC 1101's central black hole, the way a marble sits inside a sports stadium, not at the edge of the stadium, not somewhere in the middle rows. The marble would be lost entirely, invisible against the scale of the structure surrounding it. If you wanted to build IC 1101 central black hole, using the black holes at the centers of other galaxies as raw material, you would need to merge approximately 12,500 Milky Way-sized black holes together. 12,500 of them, each containing 4 million solar masses, all compressed into a single object. That object is sitting at the center of IC 1101 right now. To understand what a black hole actually is, you need to set aside almost everything that the phrase conjures in popular imagination. Black holes are not holes. They are not empty. They are not voids. They are objects, extraordinarily dense objects, whose gravitational field is so intense that nothing, not matter, not radiation, not light itself, can escape from within a certain boundary, called the event horizon. The event horizon is not a physical surface. There is no wall there, no membrane you could touch. It is simply a mathematical boundary in space, the point of no return, the distance from the black hole's center inside which the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, anything that crosses the event horizon is permanently trapped. It will inevitably fall toward the singularity at the center, a point of theoretically infinite density where the known laws of physics cease to function in any meaningful way. The size of a black hole's event horizon depends on its mass. The relationship is straightforward: double the mass, double the radius of the event horizon. For a black hole containing 50 billion solar masses, the event horizon would have a radius of approximately 150 billion kilometers. 150 billion kilometers. Our entire solar system, measured from the Sun to the orbit of Neptune, the outermost of the 8 recognized planets, spans approximately 9 billion kilometers. The event horizon of IC 1101 central black hole is roughly 16 times larger than our entire solar system. If you place this black hole where our Sun currently sits, its event horizon would extend far beyond the orbit of Neptune, far beyond the orbit of Pluto, far into the outer reaches of the Oort cloud, where long-period comets spend most of their existence. Everything we consider our solar home, every planet, every moon, every asteroid, every comet that has ever been catalogued, would exist well inside the event horizon of this single black hole. None of it could escape, not the gas giants, not the rocky planets, not the light radiating from our Sunday. Everything within that enormous sphere would be falling irreversibly and forever toward the singularity at the center. What would it be like in the vicinity of such an object? The physics of extreme gravitational environments is among the strangest territory in all of science, a region where the equations of general relativity produce results so counterintuitive that they seem to belong to a different universe than the one we experience in daily life. And yet those results have been tested, confirmed, and incorporated into our best understanding of how the cosmos actually works. Time passes differently in strong gravitational fields. This is not a metaphor. It is not a poetic way of describing subjective experience. It is a physical fact, measurable with precise instruments, predicted by Einstein's general theory of relativity and confirmed repeatedly by experiment. Clocks run slower in stronger gravitational fields. A clock sitting near the surface of the Earth runs measurably slower than an identical clock in orbit, where gravity is slightly weaker. The difference is tiny in everyday circumstances, but it is real, and GPS satellites must account for it in their calculations, or their position measurements would drift into uselessness within hours. Near the event horizon of a supermassive black hole, the effect is not tiny, it is extreme. An observer hovering just outside the event horizon of IC 1101 central black hole, somehow managing to maintain their position against the overwhelming gravitational pull, would experience time at a dramatically different rate than an observer watching from far away. A year passing for the distant observer might correspond to only minutes or seconds or less for the one hovering near the horizon. The universe outside would appear to be running at tremendous speed, stars racing through their lives, galaxies evolving in what seems like moments. And for an observer falling through the event horizon, the experience depends on how massive the black hole is. For stellar mass black holes, objects containing only a few times the mass of our Sun, the tidal forces at the event horizon are so intense that a falling object would be stretched vertically and compressed laterally in a process physicists have named spaghettification. The difference in gravitational pull between your head and your feet would be so enormous that your body would be drawn out into a long, thin strand of matter before you ever cross the horizon. But for a supermassive black hole of IC 1101 scale, something different happens. The event horizon is so large, and the curvature of space-time at that boundary is therefore so gentle that a falling observer might cross the event horizon without feeling anything unusual at all. No dramatic sensation, no obvious boundary. Simply a threshold crossed, invisible and unmarked, after which the laws of physics ensure that no path leads outward. The singularity waits ahead, inevitable and inescapable. But the crossing itself might be entirely unremarkable. You would not know you had passed the point of no return until it was far too late to matter. The black hole at IC 1101 center is not, at this moment, actively devouring enormous quantities of matter. It is relatively quiet. There is no brilliant accretion disk currently swirling around it, no powerful beam of radiation blazing outward to announce its presence to the distant universe. The monster is dormant. But it was not always so, and the evidence of its more violent past is written clearly in the environment surrounding it. Astronomers have detected a radio source at IC 1101 center, catalogued as PKS 1508+059. This radio emission comes from relativistic jets, narrow beams of plasma and magnetic field, accelerated to very nearly the speed of light and ejected outward from the vicinity of the black hole along its rotation axis. These jets are powered by the interaction of the black hole's rotation with the surrounding magnetic fields, and they carry enormous amounts of energy away from the center of the galaxy. When X-ray observatories, particularly NASA's Chandra X-ray Observatory, have examined the hot gas surrounding IC 1101 and the Abell 2029 cluster, they have found something extraordinary. There are cavities in that gas, enormous bubbles, some of them millions of light years across, carved into the surrounding intracluster medium by the energy of IC 1101's jets. These cavities are not empty in the absolute sense. They are filled with very hot, very thin plasma and tangled magnetic fields, blown outward by the jets like enormous soap bubbles expanding into the surrounding gas. The energy required to inflate these cavities is almost beyond calculation. Astronomers have estimated it to be equivalent to the total energy output of billions of stars sustained over millions of years. All of that energy released, not gradually, not distributed across a long, slow period of stellar burning, but pumped into the surrounding environment by a single black hole during episodes of intense feeding activity. These cavities are the footprints of IC 1101's past. They record periods when the central black hole was consuming gas at tremendous rates, converting that mass into energy with an efficiency that no other process in the universe can match, and blasting that energy outward into the surrounding cluster. During those active periods, IC 1101's center would have blazed as a quasar, one of the most luminous objects in the observable universe, outshining all 100 trillion of its stars combined. That activity has now subsided. The gas supply that once fed the black hole has been exhausted or heated beyond the point where it can easily fall inward. The jets still exist, but they are weaker than they once were. The radio emission detectable but not overwhelming. The black hole has entered a kind of enforced quiet, a dormancy imposed by the depletion of its food supply. But the quiet is not complete, and the influence of the black hole on IC 1101 continues even now, in ways that are subtle but profound. The relationship between a galaxy and the supermassive black hole at its center is one of the most fascinating and least intuitively obvious discoveries in modern astrophysics. For most of the 20th century, Astronomers thought of central black holes as passive objects. They were there, certainly, but their influence was thought to be limited to the innermost regions of their host galaxies. The rest of the galaxy, the hundreds of billions of stars in the outer disk and spiral arms, was assumed to be essentially unaffected by whatever happened at the center. That picture turned out to be wrong. What astronomers discovered, gradually over the course of several decades of observation and theoretical work, is that supermassive black holes and their host galaxies are locked in a relationship of mutual regulation. Each shapes the development of the other. Each constrains what the other can become. The black hole does not simply sit passively at the center of its galaxy. It actively governs the galaxy's evolution, acting as a kind of thermostat that regulates how much star formation is permitted to occur. The mechanism works as follows. Hot gas in the surrounding cluster environment gradually cools over time, radiating away its energy as X-rays. As it cools, it becomes denser and begins to fall inward toward the central galaxy. If enough of this cooling gas reaches IC 1101's inner regions, it can collapse to form new stars, potentially reigniting the star formation that has otherwise ceased throughout the galaxy. But as this gas falls toward the center, some of it inevitably approaches the supermassive black hole. The black hole consumes a fraction of it, and in doing so releases energy in the form of jets and radiation. That energy heats the surrounding gas, causing it to expand back outward. The very act of the black hole consuming a small amount of infalling material produces enough energy to reheat and push back the much larger reservoir of gas that was falling inward. The cooling is interrupted. The star formation that was about to begin is prevented. This feedback loop, in which the black hole regulates the gas supply that would otherwise fuel star formation, is now understood to be one of the primary reasons why massive elliptical galaxies like IC 1101 are not forming stars today. Without this mechanism, cooling flows would deliver enough cold gas to the center of the cluster to trigger substantial star formation rates, potentially hundreds of solar masses worth of new stars per year. With the black hole acting as a thermostat, that gas is continually reheated before it can collapse. The largest galaxy ever found is being kept in a state of enforced sterility by the black hole at its center, not through any intention, not through any purposeful action, but simply through the blind operation of physical law. Energy released by accretion heats gas. Heated gas cannot form stars. The black hole feeds less. The gas cools again. The cycle begins once more. A feedback loop operating across millions of light years, regulated by physics, maintaining an equilibrium between the largest galaxy in its cluster and the most massive black hole we have ever found at the center of such a structure. How did this black hole grow so large? The answer leads back, once again, to IC 1101's history of galactic cannibalism. Every large galaxy has a supermassive black hole at its center. When IC 1101 consumed another galaxy, it did not merely absorb that galaxy's stars and gas. It eventually absorbed that galaxy's central black hole as well. And when two supermassive black holes find themselves inside the same galaxy, what follows is a process as violent and dramatic on its own scale as any of the galactic mergers that brought them together. Initially, the two black holes are separated by enormous distances, each one carrying the orbital momentum of the galaxy it came from. They do not immediately find each other. Instead, they settle toward the center of the merged galaxy through the same dynamical friction that brings galaxies together, losing energy through gravitational interactions with surrounding stars. This process takes hundreds of millions of years, but eventually, the two black holes get close enough to form a binary system, orbiting around each other in an ever-tightening spiral. As they orbit, they radiate gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein's general relativity, and first directly detected in 2015 by the LIGO observatories, which measured waves produced by the merger of two stellar mass black holes approximately 1 billion light-years away. The detection was announced in February of 2016, and it was immediately recognized as one of the most significant scientific discoveries of the century. A new sense with which to perceive the universe, one that operates not through light but through the geometry of space and time itself. For stellar mass black holes, the process of gravitational wave emission and the resulting orbital decay takes a relatively short time on cosmic scales. For supermassive black holes, the time scales are longer, but the eventual outcome is the same. The orbit shrinks. The two black holes spiral ever closer, completing their orbits faster and faster as they approach. And then, in a final catastrophic event that releases more energy than all the stars in a typical galaxy, they merge. The gravitational waves produced by the merger of two supermassive black holes are among the most powerful events the universe is capable of generating. They ripple outward at the speed of light, stretching and compressing space as they pass, carrying the record of the collision across billions of light years. Future space-based gravitational wave observatories, particularly the planned LISA mission currently under development by the European Space Agency, will be sensitive enough to detect mergers of supermassive black holes when they occur. LISA, if it launches as planned in the 2030s, may actually observe events similar to the mergers that built IC 101's central black hole over billions of years. We will be able to hear, in a sense, the music of colliding giants. IC 101's central black hole has experienced this process dozens of times. Each merger with another galaxy brought another supermassive black hole into the system. Each pair of black holes spiraled together and ultimately merged, adding their combined mass to the growing monster at the center. Each merger also produced the gravitational scouring that scattered stars from IC 101's core, the process that left the galaxy's innermost region unexpectedly sparse despite containing more mass than most entire galaxies in the observable universe. 40 billion to 100 billion solar masses, built over billions of years, merger by merger, feeding event by feeding event, growing larger with each galaxy consumed, each black hole absorbed, each burst of accretion that lit IC 101's center like a beacon visible across hundreds of millions of light years. And now it waits, dormant but not gone, massive beyond comprehension, surrounded by the cooling gas of the intracluster medium, occasionally stirred to brief activity when a star wanders too close or a pocket of cold gas falls inward from the cluster environment, maintaining its quiet regulation of the galaxy around it, ensuring that IC 101's final generation of stars burns on in ordered silence, unjoined by any new arrivals. The largest black hole we have found in the largest galaxy we have ever discovered, both of them in their different ways at the end of their most active days. Both of them still enormous, still present, still shaping the space around them through the simple, irresistible authority of mass. We have not yet asked what the future holds for them. That question requires us to travel further in time than we have gone in space. Further than the billion light years we crossed to reach IC 101, into a future so remote that the present moment, and everything we currently understand as the history of the universe, will seem by comparison like the first breath of something only beginning. But before we follow IC 101 into that future, we need to stop. We need to simply stand here, at this point in the journey, and try to feel the scale of what we have been describing, because we have been moving through these numbers quickly, and numbers move too easily through the mind without leaving the impression they deserve. The next part of this journey is devoted entirely to that. Stop for a moment. Before we continue into the future of IC 101, before we follow this dying giant across the billions of years still ahead of it, we need to pause here and do something that science alone cannot do for us. We need to try to feel what we have been describing, not understand it in the abstract, intellectual sense, not process it as a sequence of large numbers moving through the mind without friction, but actually feel it somewhere beneath the level of language, in the place where genuine awe lives. The numbers we have been using are accurate. 100 trillion stars, 4 to 6 million light years, 50 billion solar masses, compressed into a region 16 times the size of our solar system, 1 billion light years of distance. These figures are as precise as our instruments and methods currently allow, but precision is not comprehension. You can recite a number perfectly and still have no real sense of what it means. The human mind did not evolve to handle quantities at this scale. Nothing in the environment our ancestors navigated over millions of years of evolution required the ability to genuinely grasp 100 trillion of anything. We count well up to perhaps a few dozen. We reason adequately about hundreds and thousands. Beyond that, the numbers become symbols, placeholders for magnitudes that our cognition acknowledges but cannot truly inhabit. So let us try something different. Let us try to build these numbers from the ground up, using objects and experiences that your body and your senses already know. Begin with the speed of light. Light travels at approximately 186,000 miles per second. In a single second, a photon of light can travel from New York to Los Angeles and back again roughly 33 times. In 8 minutes and 20 seconds, light travels from the surface of the sun to the surface of the Earth. In just over 1 second, it travels from the Earth to the Moon. The speed of light is the fastest speed at which anything in the universe is permitted to travel. It is the cosmic speed limit, enforced without exception by the structure of space-time itself. Now, IC 1101 is approximately 4 to 6 million light-years across. That means light, traveling at 186,000 miles per second, every second of every minute of every hour, without pause, without slowing, without any interruption whatsoever, would take 4 to 6 million years to cross IC 1101 from one edge to the other. 4 to 6 million years. The entire evolutionary history of the human genus, from the earliest Homo habilis fashioning crude stone tools on the African savanna to the moment you are experiencing right now, spans approximately 2 to 3 million years. If you set a photon of light in motion at one edge of IC 1101 at the moment the first recognizably human creatures appeared on Earth, that photon would not yet have reached the other side. Our entire history as a genus, everything that makes us what we are, would fit inside the crossing time of this single galaxy, with room remaining for another genus of humans to rise and fall on the other side. Now, let us try the Voyager 1 spacecraft. Voyager 1 was launched by NASA in September of 1977. It has been traveling continuously ever since, for nearly 50 years, moving at approximately 38,000 miles per hour relative to the Sunday. It is currently the most distant human-made object ever built. It has crossed the heliopause, the boundary where the sun's influence gives way to interstellar space, and it is now traveling through the void between stars. 38,000 miles per hour sounds fast. By any human standard, it is almost incomprehensibly fast. A commercial aircraft travels at roughly 500 miles per hour. Voyager 1 is moving at 76 times that speed. If you could somehow board Voyager 1 and fly it from New York to Los Angeles, the journey would take approximately 4.5 minutes. But 38,000 miles per hour, in the context of interstellar distances, is essentially stationary. At Voyager 1's current speed, it would take approximately 80,000 years to reach Proxima Centauri, the nearest star to our Sun, which sits only 4.25 light-years away. Not 4 million light-years, 4.25 light-years. The nearest star, 80,000 years. To cross the Milky Way at Voyager, one's speed would require approximately 2 billion years. To cross IC 1101 would require somewhere between 80 billion and 120 billion years. The universe itself is approximately 13.8 billion years old. To cross IC 1101 at the speed of our fastest spacecraft would take roughly 8 to 9 times longer than the universe has existed. You could wait for the universe to reach its current age, and then wait that long again, and then wait that long again, and then wait that long again, and you would still not have crossed this single galaxy. There is no vehicle we could build, there is no propulsion system we could devise, there is nothing within the boundaries of known physics that would allow a human being to cross IC 1101 within any time frame connected to human experience. It is not a matter of technology, it is a matter of what the universe permits. Let us try a different approach. Let us think about counting. You are a reasonably fast counter. With concentration, You can count at approximately 2 to 3 numbers per second. But let us be generous. Let us say you count 1 number per second, steadily and without stopping, and let us say you never need to sleep, never need to eat, never grow tired, never make a mistake. You simply count 1 number every second, indefinitely. To count to 1 million at that rate would take approximately 11.5 days. To count to 1 billion would take approximately 31.5 years. To count to 1 trillion would take approximately 31,700 years, longer than all of recorded human history. To count to 100 trillion, the number of stars in IC 1101 would take approximately 3,170,000 years. If you had begun counting at the moment the first stone tools appeared in the archaeological record of human prehistory, you would still have millions of years of counting ahead of you. Agriculture would not have been invented yet in terms of your count. Writing would not have been invented. Every civilization that has ever existed on Earth would rise and fall while you are still working your way through the first fraction of IC 1101's stellar population. 1 number per second for 3 million years. That is how many stars are in this galaxy. Now, let us think about photographs. Imagine you have a camera capable of capturing 1 image per second, and you have decided to photograph every star in IC 1101 individually. 1 photograph, 1 star, 1 second, continuously, without pause. How long would this project take? 3,170,000 years. The same number, because the photography rate and the counting rate are the same, 1 per second. In the time it would take to photograph every star in IC 1101, the continents of Earth would have shifted into configurations unrecognizable from their current positions. The Himalayas might have eroded to gentle hills, new mountain ranges might have risen elsewhere, the Atlantic Ocean might be significantly wider or narrower. The entire geological face of our planet would be transformed beyond recognition multiple times over before the last photograph was taken. Let us try sand. The beaches of Earth contain an enormous number of grains of sand. Estimating the precise figure is difficult because beaches vary enormously in depth and extent, but the commonly cited figure, based on careful estimates by researchers at the University of Hawaii, is approximately 7.5 quintillion grains of sand on all of Earth's beaches combined. 7.5 quintillion is 7.5 followed by 18 zeros. 100 trillion is 1 followed by 14 zeros. IC 1101's 100 trillion stars is therefore significantly fewer than the grains of sand on Earth's beaches, but it is in the same general order of magnitude. It is the kind of number that, if you could somehow physically represent it, would fill an entire coastline many times over. But here is what makes this comparison striking. Every single one of those stars is a sun, not a grain of sand, not a symbol, not an abstraction. A nuclear furnace, burning hydrogen into helium, radiating energy outward in every direction, potentially warming planets, potentially illuminating the surfaces of worlds where something looks up and wonders what it is looking at. The grains of sand on Earth's beaches are inert. They do not burn. They do not radiate. They do not pull the surrounding space into orbit around them with the force of their gravity. Every one of IC 1101's 100 trillion stars does all of these things simultaneously right now and has been doing them for billions of years. Now, let us think about the light itself. The photons of light reaching our telescopes from IC 1101 today began their journey more than 1 billion years ago. Let us try to understand what that means in terms of Earth's history. 1 billion years ago, Earth was approximately 3.5 billion years old. Life had existed on this planet for roughly 2.5 billion years already, but it had not yet made the transition to complex multicellular forms. The most advanced organisms on Earth at that time were microbial mats and simple colonies of single-celled organisms, spread across shallow seas in a world that looked nothing like the one we inhabit. There were no fish, there were no insects. There were no plants in any form recognizable today. There were no animals of any description. The atmosphere had a different composition. The continents were gathered into a configuration called Rodinia, a supercontinent that existed roughly 1 billion years ago. before breaking apart and drifting into new arrangements over the hundreds of millions of years that followed. The moon was slightly closer to Earth than it is today, making tides somewhat stronger. The day was slightly shorter, Earth rotating a little faster than it currently does. It was an alien world, and it was on that alien world, at that moment in deep time, that the photons now arriving at our telescopes first left IC 1101. Those photons have been traveling through intergalactic space every moment since. While Earth developed complex life, while the first animals evolved in the oceans, while the first creatures crawled onto land, while the dinosaurs rose and fell, while the first mammals diversified, while the first primates appeared, while the first humans stood upright and looked at the sky, that light was crossing the void between galaxies, patient and unchanging, carrying information about IC 1101 as it existed before complex life had ever taken a breath on this world. And it is only now arriving. Let us try to scale this down to something you can hold in your hands. Imagine shrinking the Milky Way to the size of a standard dinner plate, 10 inches across. On that scale, every inch represents 10,000 light-years of actual space. Our solar system, the Sun, and all its planets would be an object far too small to see with the naked eye. Even with a magnifying glass, you would struggle to locate it. We would be invisible on the surface of the dinner plate, somewhere between the center and the edge, in a region indistinguishable from any other region at this scale. Now, on that same scale, what is the size of IC 1101? IC 1101 would be approximately 40 to 60 dinner plates laid edge to edge. Not a larger plate, not a platter. 40 to 60 dinner plates arranged in a line, spanning roughly 30 to 50 feet of physical space. Our galaxy, the object that already seemed impossibly vast, the structure that takes 100,000 years for light to cross, the home of 200 to 400 billion stars, is a single dinner plate in this comparison. IC 1101 is the length of a room. Our sun, our solar system, everything we have ever directly experienced or will ever experience, is a point too small to see on a single dinner plate in a room filled with 40 to 60 of them. Now let us think about what dark matter adds to this picture. The stars of IC 1101, all 100 trillion of them, represent only a fraction of the galaxy's actual mass. Like all large galaxies, IC 1101 is embedded in a vast halo of dark matter, material that does not emit light, does not absorb light, and does not interact with normal matter through any force except gravity. We cannot see dark matter directly. We know it exists because of its gravitational effects on the stars and gas we can see, and because without it, the rotation rates of galaxies would be impossible to explain under the known laws of physics. In a typical large galaxy, dark matter accounts for roughly 90% of the total mass. The stars and gas that we can observe, the things that make a galaxy visible to our instruments, are the minority. The vast, invisible dark matter halo surrounding them is the majority. For IC 1101, astronomers estimate that the total mass, including dark matter, may be as high as 100 quadrillion solar masses. 100 quadrillion. The stellar body of IC 1101, already 4 to 6 million light-years across, is embedded within a dark matter halo that likely extends tens of millions of light-years in every direction. The visible galaxy, enormous as it is merely the bright core of a structure far larger still, one that stretches through space in all directions, invisible and undetectable, except through the curvature it produces in the paths of everything around it. What we see when we image IC 1101 is not the whole of IC 1101. It is only the part that emits light. The true extent of this structure, the full gravitational reach of this object, is larger by a significant margin than anything our telescopes can directly observe. We are seeing the lit portion of something even greater, the way you might see the glow of a city on the horizon without seeing the city itself. And finally, let us think about communication. Suppose that somewhere in IC 1101, on one of the hundreds of trillions of possible planets, orbiting one of its 100 trillion stars. There is an intelligent civilization, and suppose that civilization decides to send a message, a signal of some kind, traveling at the speed of light, directed across the width of their galaxy toward whatever might be listening on the other side. That message, traveling at the fastest speed the universe permits, would take 4 to 6 million years to arrive. If the civilization sending the message had been doing so since the moment the first stone tools appeared in the human archaeological record, their signal would still be in transit. It would not yet have reached the other side of their own galaxy. Any civilization receiving such a message and choosing to reply would send a reply that would take another 4 to 6 million years to return. A single exchange of messages, one question and one answer, would span 8 to 12 million years. The entire span of time since the genus Homo first appeared on Earth, twice over, consumed by a single conversation across the width of one galaxy. This is not a limitation of technology, it is a limitation of physics, of the speed of light and the size of the universe, and the distance between things. No civilization, no matter how advanced, no matter how long-lived, no matter how capable, can overcome the simple fact that space is vast and light moves at a fixed speed through it. IC 1101 is a place where even light is humbled by distance, where even the fastest thing in the universe needs millions of years to cross from one side to the other, where the scale of a single object exceeds any frame of reference built from human experience and requires us to construct new frames entirely from scratch, using only the raw materials of imagination and the willingness to sit quietly with numbers that refuse to be small. 100 trillion stars, 4 to 6 million light-years, 50 billion solar masses in a single black hole, 1 billion years of light travel time, 90% of the mass invisible to every instrument we possess. These are not approximations, they are not dramatizations, they are, as precisely as our science currently allows us to determine what IC 1101 is, and somewhere in the direction of the constellation Virgo, utterly indifferent to whether any mind in the universe has paused to consider it, this galaxy continues to exist. Its 100 trillion stars continue to burn, its ancient black hole continues to wait, its dark matter halo continues to curve the space around it. It does not know we are watching, it does not know we exist, and yet we have found it, measured it, and sat here in the quiet, trying to feel what it means. That, in itself, is something worth holding on to. But we have not yet followed this galaxy into its future, and the future of IC 1101 is, in some ways, the most profound part of this entire journey, because it is not only IC 1101's future, it is the future of everything. Everything we have discussed so far has been about the past and the present. The formation of IC 1101, its growth through billions of years of galactic cannibalism, the physics of its central black hole, the scale of its stellar population, all of it describes something that has already happened, or is happening now, in the narrow window of cosmic time that we occupy. But IC 1101 has a future, a long one, longer than anything in human experience has prepared us to contemplate. And following that future to its conclusion requires us to travel further in time than we have yet traveled in space, out past the point where stars exist, past the point where atoms exist, into a darkness so complete and so permanent that the word darkness no longer quite captures it. This is where the story of the largest galaxy ever found ultimately leads, not to triumph, not to continued dominance, but to a silence so absolute that even the concept of silence requires something to contrast itself against, and there will be nothing left to provide that contrast. Let us follow IC 1101 into what comes next. The first force we need to understand is one that is already at work, reshaping the large-scale structure of the cosmos at this very moment. It is called dark energy, and it is among the most mysterious and consequential discoveries in the history of science. For most of the 20th century, cosmologists assumed that the expansion of the universe, the outward movement of all galaxies away from all other galaxies that has been occurring since the Big Bang was gradually slowing down. This seemed like a reasonable assumption. The universe contains enormous amounts of matter, and matter exerts gravitational attraction. All of that gravity, distributed across the cosmos, should act as a brake on the expansion, pulling everything back toward everything else, gradually decelerating the outward movement of galaxies over time. In 1998, two independent teams of astronomers set out to measure exactly how much this deceleration had occurred. They were using a particular type of exploding star, called a Type Ia supernova, as what astronomers call a standard candle. Type Ia supernovae occur when a white dwarf star, the dense remnant of a sun-like star that has exhausted its fuel, accumulates too much mass from a companion star and undergoes a catastrophic thermonuclear detonation. Because the conditions triggering this detonation are broadly similar from one event to another, these explosions reach roughly the same peak luminosity each time. By measuring how bright a Type Ia supernova appears and comparing it to how bright it should be at a given distance, astronomers can calculate distances to galaxies hundreds of millions and even billions of light years away. Both teams were expecting to measure a universe that was slowing down. Instead, they found the opposite. The universe was not decelerating, it was accelerating. Distant galaxies were receding from us faster than closer ones, and the rate of recession was increasing over time. Something was pushing the universe apart, not pulling it together. Something was counteracting gravity on the largest scales, driving an expansion that grew faster with every passing eon. That something was given the name dark energy, not because it is dark in any visual sense, but because it is invisible to every instrument we possess, and its nature remains entirely unknown. We know that dark energy makes up approximately 68% of the total energy content of the observable universe. We know that it acts as a kind of negative pressure, causing space itself to expand at an accelerating rate. And we know that its effects will become increasingly dominant as the universe ages and ordinary matter becomes more and more diluted by the expansion. Beyond that, we know almost nothing. Dark energy might be a property of empty space itself, a constant energy density that fills the vacuum uniformly throughout the cosmos. It might be a dynamic field that changes over time, stronger in some eras than others. It might even be a signal that our understanding of gravity at cosmological scales is incomplete and requires fundamental revision. After more than 2 decades of intense theoretical and observational effort, the nature of dark energy remains one of the deepest unsolved problems in all of physics. What we do know is what it will do to IC 1101 and to everything else in the universe. Right now, IC 1101 sits at the center of the Abell 2029 galaxy cluster, surrounded by hundreds of other galaxies, all bound together by their mutual gravitational attraction. The cluster as a whole is gravitationally stable. The expansion of space is pushing distant objects away, but within the cluster, where gravity is strong enough to hold things together, the member galaxies continue to orbit around their shared center of mass, interacting with each other, occasionally merging, slowly evolving. This will continue for a very long time. Roughly 100 billion years from now, the expansion of space will have accelerated to the point where galaxies outside of gravitationally bound structures begin to disappear over what cosmologists call the cosmic horizon. The cosmic horizon is the distance beyond which objects are receding from us faster than light can travel toward us. Objects beyond that horizon are not simply very far away, they are permanently and irreversibly beyond reach. No signal, no force, no influence of any kind can ever bridge that gap, because the space between here and there is expanding faster than the fastest thing that can cross it. As this horizon closes in, the observable universe will shrink, not because the universe itself is getting smaller, but because the portion of it that is causally connected to any given point in space, the portion from which light can ever reach that point, will contain fewer and fewer objects. One by one, distant galaxy clusters will fade from view, their light stretched by the expansion until it falls below any detectable threshold, their galaxies carried beyond the horizon into permanent cosmic isolation. From IC 1101's perspective, the sky will begin to empty. The process will be gradual at first, imperceptible on any timescale a civilization could observe, but over billions of years, the number of galaxies visible from IC 1101 will decline. The vast cosmic web that currently connects our corner of the universe to the larger structure of galaxy filaments and voids and superclusters will dissolve as the threads of that web are stretched beyond any meaningful connection. What was once a universe teeming with 2 trillion galaxies will become, for any observer within a gravitationally bound structure, a universe containing only the local cluster. The rest of the cosmos, everything beyond the cluster's gravitational reach, will have vanished. Within the Abell 2029 cluster itself, things will continue somewhat longer. The hundreds of galaxies bound together there will keep orbiting, keep interacting, keep occasionally merging for tens of billions of years beyond the point where the rest of the universe has gone dark. IC 1101 may consume a few more of its cluster companions during this period, growing marginally larger, even as the universe outside the cluster becomes inaccessible. But eventually, even the galaxies within the cluster will exhaust their orbits. Dynamical friction, the same process that caused the merger of galaxies throughout IC 1101's history, will continue to drain energy from the orbital motions of the remaining cluster members. They will spiral inward, one by one, falling toward the cluster center, where IC 1101 waits. Over hundreds of billions of years, the cluster will consolidate, its hundreds of member galaxies gradually merging into a single enormous structure, larger even than IC 1101 is today, sitting alone in an otherwise empty and invisible universe. A single island of matter in a darkness that stretches without boundary in every direction. The night sky, if any observers still existed on any planet within this final merged structure, would show only the stars of their own galaxy. Nothing else. No smudged patches of light indicating distant galaxies. No faint glow of the cosmic web on the horizon, just the stars of the local structure, burning against a backdrop of absolute black. The rest of the cosmos, 2 trillion galaxies worth of stars and gas and dark matter, would be gone, not destroyed. Simply unreachable, carried beyond the horizon by the relentless expansion of space, their light never to arrive. The universe will still be there, in some sense, but it will be unknowable, invisible, as effectively absent as if it had never existed. And then the stars will begin to go out. This process has already begun, in a sense. Stars have been dying throughout the history of the universe, exploding as supernovae or fading quietly into white dwarfs. But new stars have been forming to replace them, born from clouds of gas collapsing under gravity. The net result, over the current age of the universe, has been a roughly stable population of stars across the cosmos, with star formation rates declining gradually as gas supplies are depleted. Approximately 100 trillion years from now, the last new star will form anywhere in the universe, not in IC 1101, which has already ceased forming stars, but in the remaining pockets of gas elsewhere in the cosmos. The final stellar nurseries will exhaust their material. No new fusion reactors will ignite. The era of star formation will be over, permanently and irrevocably, and the universe will enter what cosmologists call the degenerate era, an age dominated not by living stars, but by their remnants. The most massive stars in IC 1101's population burned out billions of years ago. The enormous blue giants and supergiants that once blazed at IC 1101's formation exhausted their fuel in millions of years, exploding as supernovae and leaving behind neutron stars and black holes. Stars similar to our Sun, which have lifetimes of approximately 10 billion years, have been dying throughout IC 1101's history. Many of them have already passed through the red giant phase, expanding to enormous size before shedding their outer layers as planetary nebulae and contracting into white dwarfs, dense spheres of electron-degenerate matter, roughly the size of Earth, but containing the mass of a star. What remain in IC 1101 101's future, burning for incomprehensibly long periods, are the red dwarfs. The smallest stars in the universe, objects containing perhaps 8 to 40% of the sun's mass, burning their hydrogen so slowly and so efficiently that some of them will shine for 10 trillion years. 10 trillion years. The current age of the universe is approximately 13.8 billion years. A red dwarf star born at the same time as our sun will still be burning long after the sun has become a cold, dark remnant. It will still be burning longer after that. The smallest red dwarfs will still be shining when the universe is 700 times its current age. But even they will eventually exhaust their fuel. One by one, across timescales that make the current age of the universe seem like an opening breath, the red dwarfs of IC 1101 will consume their last reserves of hydrogen and go dark. They will not explode. They will simply fade, their surfaces cooling from red to infrared to nothing, their cores contracting into white dwarfs. The last light in IC 1101 will be the dim red glow of the final red dwarf, burning in a galaxy that has been dark in every other corner for trillions of years. And then that light, too, will go out. What remains after the stars are gone is a galaxy of ghosts. White dwarfs, drifting through the dark, neutron stars, spinning silently in the void, their lighthouses of radio emission dimming as they slow over trillions of years. Black holes of every size, from the stellar remnants of individual massive stars to the supermassive monster at IC 1101 center, all of them moving through a darkness, unbroken by any source of light, orbiting through a structure that was once the most luminous galaxy humanity had ever found, and is now a graveyard for the remnants of 100 trillion dead suns. This is the universe approximately 100 trillion years from now. Not a dramatic end, not an explosion or a collapse. Just a slow, patient, irresistible dimming star by star across timescales so vast that the entire current age of the universe is a rounding error. The silence will be complete. But even this is not the end, because the matter that makes up white dwarfs, neutron stars, planets, and everything else in the universe may not be permanent. Music. Many theories of particle physics predict that protons, the fundamental building blocks of atomic nuclei, and therefore of all ordinary matter, are not truly stable. They may eventually decay over timescales so long that they make the lifespan of the universe seem brief. The predicted half-life of the proton, in many theoretical frameworks, is somewhere around 10 to the 34th power years or longer. That is a 1 followed by 34 zeros. It is a span of time so vast that writing it out in full requires more zeros than there are atoms in the observable universe. If protons decay on this timescale, then, over the course of the subsequent eons, the white dwarfs and neutron stars and planets that comprise IC 1101's remains will gradually dissolve. Not through any dramatic process. Simply through the slow, random decay of their constituent protons, one by one, releasing a tiny burst of energy each time, until the object that contained them has dissolved entirely into a diffuse haze of radiation and lighter particles. The matter that once made up 100 trillion stars, the carbon and oxygen and iron and silicon that was forged in stellar cores across billions of years of nuclear fusion, the material that made up not only stars but the planets around them, and, on at least one of those planets, the bodies of living creatures who looked up and wondered at the sky, all of that matter will eventually dissolve, quietly, without witness, over timescales that no number in common use can adequately represent. What remains after proton decay has run its course are the black holes. Black holes do not decay through proton decay. They are not made of protons in any meaningful sense. They are made of space-time curvature, of gravity so intense that it has warped the geometry of space beyond any ordinary description, and they will persist long after everything else in IC 1101 has dissolved. But they will not persist forever. In 1974, the British physicist Stephen Hawking made one of the most surprising theoretical discoveries of the 20th century. He showed that black holes, contrary to their name and popular description, are not perfectly black. They glow, very faintly, At a temperature that depends on their mass, they emit a slow trickle of radiation, now called Hawking radiation, through a quantum mechanical process occurring near the event horizon. The mechanism is subtle and deeply rooted in the strange behavior of quantum fields near extreme gravitational environments. In the quantum mechanical description of empty space, the vacuum is not truly empty. It is filled with constant fluctuations, pairs of virtual particles continuously appearing and annihilating each other in intervals so brief they are permitted by the uncertainty principle. Near a black hole's event horizon, something unusual can happen. One member of such a pair can fall through the horizon into the black hole while the other escapes into space. The escaping particle carries away a tiny amount of energy. The black hole, having absorbed the particle that fell in with slightly negative energy, loses a correspondingly tiny amount of mass. The rate at which a black hole loses mass through Hawking radiation is inversely proportional to the square of its mass. Small black holes lose mass quickly and eventually evaporate in a final burst of radiation. Large black holes lose mass so slowly that the process is almost unimaginably gradual. For a black hole containing the mass of our Sun, evaporation through Hawking radiation would take approximately 10 to the 67th power years, a 1 followed by 67 zeros. For the supermassive black hole at IC 1101 center, containing somewhere between 40 billion and 100 billion solar masses, the evaporation time is correspondingly longer. The calculation yields something in the vicinity of 10 to the 100th power years, a googol of years, a 1 followed by 100 zeros. To put this in some kind of perspective, if you wrote out that number in full, the string of digits would be longer than the number of atoms in the observable universe. It is not merely a large number. It is a number so large that our ordinary intuitions about large numbers provide no guidance whatsoever. The entire history of the universe, from the Big Bang to the death of the last star, all 100 trillion years of it, would not register as a measurable fraction of this duration. It would be, compared to a googol of years, immeasurably smaller than a single atom compared to the observable universe. And yet, eventually, after a googol of years has passed, the black hole will be gone. The last of IC 1101 substance, the final remnant of the largest galaxy humanity has ever found, will have evaporated in a faint burst of Hawking radiation, dispersing its last energy into a universe so cold and so dark and so empty that there is nothing left to absorb it. The radiation will simply spread outward, cooling as it travels, joining the background hum of an almost featureless cosmos. And then there will be nothing. No stars, no white dwarfs, no neutron stars, no black holes, no atoms, no matter of any kind. Only the residual warmth of Hawking radiation and particle decay, cooling asymptotically toward absolute zero in a universe that will expand forever, growing colder and darker and more diffuse with every passing moment, approaching but never quite reaching the perfect equilibrium of heat death. This is the fate of IC 1101. This is the fate of everything. Stand here for a moment and let that settle. 100 trillion stars, 4 to 6 million light years, 76 major mergers, a black hole containing 50 billion solar masses, a billion years of light travel time just to reach our telescopes. All of it, eventually, gone. Not because something went wrong, not because of any failure or catastrophe or external force acting against it, simply because the laws of physics, operating without prejudice, without preference, without any particular interest in the outcome, tend toward increasing disorder over time. The universe builds complexity slowly and destroys it inevitably. IC 1101 is the most extreme example of complexity the universe has assembled at the galactic scale, and it will follow the same trajectory as everything else, from the simplest atom to the largest structure, the long, slow arc from order to disorder, from light to darkness, from something to nothing. This might seem like a reason for despair. It might seem like the story of IC 1101 is ultimately a story of futility, that the billion years of light it sent toward us, and the 50 billion solar masses in its black hole, and the 100 trillion fires burning in its body all lead to the same end that everything leads to, and that end renders all of it meaningless. But I do not think that is the right way to read this story. The right way to read it requires us to make one final journey, not through space and not through the future, but through something smaller and stranger and more important than either, through the question of what it means that we know any of this at all. Return for a moment to William Herschel. It is June of 1790. He is 51 years old, suspended in a wooden scaffold above his garden in Slough, England, in the cold dark of a clear night. His eye is pressed to the eyepiece of the largest telescope in the world. Below him, his sister Caroline sits with a candle and a notebook, waiting for him to speak. He sweeps the telescope slowly across a region of sky in the direction of the constellation Virgo. He sees a faint smudge of light. He describes it. She writes it down. He moves on. He has just become the first human being in the history of our species to observe IC 1101. He did not know what he was looking at. He could not have known. The scientific understanding required to comprehend what that faint smudge actually was would not exist for another 130 years. He had no way of knowing that the light entering his eye had traveled for over 1 billion years to reach him. He had no way of knowing that the object producing that light contained 100 trillion stars spread across 4 to 6 million light-years of space. He had no way of knowing that at the center of that object sat a black hole containing 50 billion solar masses, or that the galaxy itself was the product of 76 major mergers spanning billions of years of cosmic history. He saw a smudge, or say a monster. The difference between those two statements is not merely a matter of better telescopes. Though better telescopes certainly helped, it is a matter of accumulated understanding, built layer by layer over generations of human inquiry, each generation inheriting the knowledge of the one before and adding to it, passing it forward, so that the people who came after could see further than the people who came before. William Herschel stood on the shoulders of Newton and Galileo and Kepler. Edwin Hubble stood on the shoulders of Herschel and Leavitt and dozens of others. The astronomers who measured IC 1101's true dimensions using the Hubble Space Telescope stood on the shoulders of everyone who had ever pointed an instrument at the sky and written down what they saw. This is what science actually is, at its deepest level, not a collection of facts, not a set of instruments, not even a method, though the method matters enormously. Science is a conversation across time, a relay race in which each runner carries the baton of accumulated understanding as far as they can before passing it to the next. The baton is never dropped, it only moves forward, and every generation that picks it up can see further than any generation before, not because they are smarter or more capable, but because they are standing further along a path that their predecessors spent their lives building. What we know about IC 1101 today is the current position of that baton. Someone in the future will carry it further. They will know things about IC 1101 that we cannot currently imagine, things that will make our present understanding look as incomplete as Herschel's smudge looks compared to what we know now. And someone after them will know more still. The conversation does not end. It only deepens. In 1995, the Hubble Space Telescope was pointed at a tiny patch of sky in the constellation Ursa Major. The patch was chosen specifically because it appeared to contain nothing. No bright stars, no known galaxies, just an apparently empty region of sky, selected precisely for its emptiness. The telescope gathered light from that patch for 10 consecutive days, building up an exposure of extraordinary depth. The resulting image was called the Hubble Deep Field. In that image, which covered an area of sky roughly equivalent to a grain of sand held at arm's length, astronomers counted approximately 3,000 galaxies, not stars, galaxies. Each one a structure containing billions or hundreds of billions or even trillions of stars, each one separated from us by distances of billions of light years, each one reduced by that distance to a faint smear of color on a photographic plate, barely distinguishable from noise. 3,000 galaxies in a patch of sky the size of a grain of sand. Subsequent deep field images went further. The Hubble Ultra Deep Field, the Hubble Extreme Deep Field, and most recently the first deep-field images from the James Webb Space Telescope, launched in December of 2021 and operational since 2022, have revealed ever greater numbers of galaxies in ever smaller patches of sky, pushing further back in time toward the first galaxies that formed after the Big Bang. The conclusion from all of these observations is the same, and it is one of the most vertiginous facts in the history of science. Everywhere we look, no matter how small the area of sky we examine, no matter how empty it appears to the naked eye, we find galaxies. The entire sky, every direction in every hemisphere, is covered by galaxies sitting behind more galaxies, receding all the way back to the edge of the observable universe. The current best estimate for the total number of galaxies in the observable universe is approximately 2 trillion. 2 trillion separate island universes, each containing billions or trillions of stars, each with its own history of formation and merger and evolution, each with its own central black hole, each potentially harboring its own collection of planets and, perhaps, its own forms of life. 2 trillion galaxies. IC 1101 is one of them. Just one. Exceptional in its size and mass, remarkable by any measure we can apply, the largest single stellar structure humanity has ever identified. And yet, in the full context of the observable universe, still just one member of a community of 2 trillion, the universe is not merely large. It is categorically, fundamentally, irrevocably beyond any scale that the word large was ever designed to describe. And yet here we are, on a small rocky planet, orbiting an ordinary star, having figured this out. Let us think about what you are made of. Every atom in your body was forged inside a star. Not metaphorically, not approximately, literally, in the precise physical sense. The carbon in your muscles, the oxygen in your lungs, the iron in your blood, the calcium in your bones, the nitrogen in your DNA. Every element heavier than hydrogen and helium that makes up the substance of your body was synthesized by nuclear fusion in the interior of a star that lived and died before our sun was born. When those ancient stars exhausted their fuel, they did not simply go dark. The most massive ones exploded as supernovae, releasing in a matter of seconds more energy than they had radiated across their entire lifetimes. Those explosions scattered the elements forged in their cores across interstellar space, seeding the surrounding gas with the raw materials for everything that came after. Over millions of years, some of that scattered material drifted and clumped, and was incorporated into new clouds of gas and dust. Eventually, some of those clouds collapsed under their own gravity to form new stars and the planets orbiting them. One of those clouds collapsed approximately 4.5 billion years ago, in a quiet region of the Milky Way called the Orion Arm. It formed our sun and the disk of material that surrounded it, from which the planets condensed over millions of years. Earth formed from that disk, a rocky world of silicates and metals in the habitable zone around a young star. Over billions of years, chemistry on that world became biology. Biology became complexity. Complexity became consciousness. And consciousness looked up. The atoms in your body are not merely related to the atoms burning in IC 1101's 100 trillion stars. They are the same kinds of atoms, forged by the same process, governed by the same physical laws, participating in the same cosmic story. The carbon that forms the backbone of your DNA is chemically identical to the carbon in the cores of stars a billion light-years away. The iron that carries oxygen through your bloodstream is the same iron that makes the cores of ancient red giants glow with a particular color as they die. You are not separate from the cosmos you observe. You are made of it. You are a local arrangement of matter that the universe has somehow produced in this particular region of space and time that is capable of turning around and looking at the universe from the inside. You are the universe become self-aware, not in any mystical sense, in the precise, physical, chemical, biological sense. The same matter, the same forces, the same laws, only here, briefly, assembled into a configuration that asks questions about itself. This is what makes the story of IC 1101 something more than a catalogue of large numbers. The large numbers are real and they matter. 100 trillion stars, 4 to 6 million light-years, 50 billion solar masses, a Google of years until the last remnant evaporates. These figures describe an actual object in an actual universe, and their accuracy is the product of genuine scientific work carried out by real human beings who spent their lives learning how to extract information from light. But the numbers are not the point. The point is, what happens when a mind encounters them? When you sit with a figure of 100 trillion stars and genuinely try, to feel the weight of it, something occurs in you that cannot be reduced to information processing. Call it awe, call it wonder, call it the particular species of humility that arises when you confront something so far beyond your ordinary frame of reference that your ordinary frame of reference simply dissolves. Whatever you call it, it is real. It is an experience, and it is, in a universe that is mostly vacuum and radiation and dark matter and expanding space-time, vanishingly rare. We do not know of any other place in the observable universe where matter has arranged itself into a configuration capable of experiencing awe. We suspect there are others. The numbers suggest there almost certainly are others, but we do not know of them. What we know of is here, this planet, this species, this moment, and in this moment, the universe has produced something that looks at IC 1101 and is moved by it. That is not nothing. That is, by any reasonable measure, extraordinary. Consider what it took to produce this moment. The universe had to exist in the first place, which required the Big Bang to occur in the precise way it did, with the precise values of physical constants that allow matter to form and stars to ignite and planets to accumulate in chemistry to become biology. If the strength of gravity was slightly different, stars would never form or would burn out too quickly for life to develop around them. If the strong nuclear force were slightly weaker, atomic nuclei would not hold together. If the cosmological constant, the measure of dark energy's strength, was slightly larger, the universe would have expanded too quickly for matter to ever clump into galaxies. The parameters that describe our universe are, within the ranges we can examine, tuned in ways that permit complexity to arise. Whether this is remarkable or expected, whether it reflects some deeper principle or merely our necessary existence in a universe where the parameters happen to work out, is a question physics cannot currently answer. But the fact remains, the parameters worked out. The universe formed, stars ignited, elements were forged, planets formed, life emerged, consciousness arose, and here we are. The entire chain of events from the Big Bang to this moment, to you sitting here contemplating IC 1101, required every prior step to occur as it did. It required our sun to form in the right region of the Milky Way. It required Earth to form at the right distance from that Sunday. It required the right chemistry to develop in the right environment over the right timescale. It required the extinction of the dinosaurs, which cleared the ecological space for mammals to diversify. It required the particular lineage of primates that led to our genus, and the particular series of evolutionary pressures that produced the cognitive architecture capable of abstract thought and scientific reasoning. Every one of those steps was contingent, none of them were guaranteed, and the result of their improbable concatenation is that the universe now contains, in this corner of an average spiral galaxy, in a modest galaxy group, creatures capable of measuring the width of IC 1101. Our own galaxy will not escape the forces that shaped IC 1101. The Milky Way participates in the same cosmic dynamics, on a smaller scale and a longer timeline, but driven by the same physics. Right now, the Milky Way is in the process of consuming several smaller galaxies. The Sagittarius dwarf galaxy has been orbiting our galaxy for billions of years and has passed through the Milky Way's disk multiple times, its stars being stripped away and incorporated into our own stellar population with each passage. Long streams of stars trailing behind this disrupted dwarf galaxy are visible to astronomers who know where to look, ghostly ribbons of stellar material marking the path of a galaxy being slowly torn apart and absorbed. The Large Magellanic Cloud, visible from the southern hemisphere as a bright patch in the night sky, is itself being drawn closer to the Milky Way, its gas being stripped away by our galaxy's gravitational pull, its stellar populations eventually destined to join our own. Even now, the Milky Way is a cannibal, quieter and slower than IC 1101, but engaged in the same fundamental process of growth through consumption. And in the future, an even more dramatic encounter awaits. The Andromeda Galaxy, currently 2.5 million light-years away, is moving toward us. Measurements from the Hubble Space Telescope and the Gaia spacecraft have refined our understanding of this approach, and while the precise trajectory carries some uncertainty, the general picture is clear. In approximately 4 to 5 billion years, the Milky Way and Andromeda will begin their first close encounter. The gravitational interaction will distort both galaxies, pulling long tidal tails of stars into intergalactic space, triggering bursts of star formation, beginning the long process of merger that will ultimately produce a single large elliptical galaxy from what are currently two spirals. That merged galaxy, sometimes called Milky by astronomers, will be smaller than IC 1101 by a significant margin. It will not have access to the rich cluster environment that allowed IC 1101 to grow through 76 major mergers. It will be a more modest giant, an elliptical galaxy of several trillion stars, sitting in a local group that will itself eventually merge into a single structure as all its member galaxies are drawn together by gravity. By the time this merger occurs, roughly 5 billion years from now, our Sun will be approaching the end of its life. It will be swelling into a red giant, its outer layers expanding outward past the orbit of Mercury, then Venus, then reaching toward Earth. The fate of our planet at that stage is uncertain. It may be engulfed entirely, its surface vaporized by the expanding solar atmosphere. It may survive the red giant phase, stripped of its oceans and atmosphere, a bare rock orbiting the hot white dwarf our Sun will eventually become. Either way, the story of Earth as a living world will have ended long before the Milky Way and Andromeda complete their merger. Whatever observers might witness that cosmic collision, they will not be us. They will be our successors in whatever form. Life on this planet, or on other worlds we may eventually reach, has taken after 5 billion years of continued evolution and history and change. That thought is both humbling and strangely comforting. The story of life does not depend on the story of Earth, any more than the story of Earth depended on any single species or any single individual. The universe is generous with its time and its possibilities. 5 billion years is a very long time, long enough for almost anything. We began this journey with a number, 100 trillion stars. We tried to feel it. We tried to build it from the ground up, using grains of sand and dinner plates and spacecraft and the speed of light. We failed, as we always will, to truly grasp it. That failure is not a deficiency. It is simply the honest result of a mind designed for a different scale, encountering the actual dimensions of the cosmos. But something happened in the attempt. In trying to comprehend IC 1101, in sitting with its dimensions and its history and its future and its ultimate dissolution into darkness, something shifted in the way the universe looks. Not because we have learned new facts, though we have, but because we have stood, for a while, in the presence of something genuinely overwhelming, and let it be overwhelming, without retreating into the comfort of abstraction. IC 1101 is dying. Its stars are the last generation it will ever produce. Its black hole will one day evaporate into nothing after a span of time so long that the concept of time itself may need to be reconsidered. Everything it contains, everything it has been and done and produced over billions of years of cosmic history, will eventually be gone. And yet, right now, at this moment in the universe's history, IC 1101 is magnificent. 100 trillion stars are burning in its body. Ancient light is streaming outward from its surface in every direction, crossing the void at the speed of light, carrying information about this object to every corner of the observable cosmos. The largest galaxy ever found by the eyes and instruments of a civilization of curious creatures on a small rocky planet more than 1 billion light-years away is, right now, shining. And we can see it, not with our eyes. It is too faint and too distant for that. But with the instruments we have built, the telescopes we have launched into orbit, the detectors we have designed, the computers we have programmed to process the signals those instruments return, with all of that, the accumulated ingenuity of generations of human beings who were curious about the sky and dedicated their lives to learning what it contained, we can see it. We have measured it. We have weighed it. We have traced its history back through billions of years and projected its future forward through trillions more. We have found the black hole at its center and estimated its mass. We have counted, imprecisely but meaningfully, the stars in its body. We have understood, at least in broad outline, how it came to be the thing it is. From a billion light-years away, using instruments carried to orbit on rockets and pointed at a tiny smudge of light that a man in a garden in Slough first noticed on a June night in 1790, without any idea what he was seeing. That reach, from the candlelit notebook of Caroline Herschel to the imaging arrays of the Hubble Space Telescope, from the faint smudge in a 19th century eyepiece to the measured dimensions of the largest galaxy in the observable universe, that reach is the story of science. It is the story of what happens when curiosity is taken seriously, when questions are pursued past the point of easy answers, when each generation refuses to accept the limits of the last. When you next go outside on a clear night and look up at the sky, find the constellation Virgo if you can. In the direction of that constellation, more than a billion light-years away, IC 1101 is sitting in the dark. You cannot see it. No human eye has ever seen it directly, or ever will, but it is there, shining with the light of 100 trillion stars, sending photons outward in every direction, some of them aimed, by the pure geometry of an isotropic universe, directly toward the eyes you are using to look for it. Those photons will not arrive in your lifetime. They will not arrive in the lifetime of your civilization or any civilization you can currently imagine. They will still be traveling when the sun has become a white dwarf and Earth is a cold, airless rock in a darkening solar system. They will still be traveling when the Milky Way and Andromeda have completed their merger and the local group has settled into its final consolidated form. But they are on their way. And the photons that left IC 1101 a billion years ago, the ones that began their journey when Earth was populated only by microbial mats in shallow seas, the ones that have been crossing the void every moment since, through the entire evolutionary history of complex life on this planet, those photons are arriving now, at this moment, at the mirrors of our telescopes, carrying the image of a galaxy as it existed before anything on Earth had eyes to see it. We are the first eyes it has ever reached. We are the first minds that have ever received its message, decoded it, understood what sent it, and been moved by the understanding. In a universe that is mostly darkness and cold and empty expanding space, in a cosmos governed by physical laws that operate without preference or purpose, in a reality that contains 2 trillion galaxies and has no apparent interest in whether any of them are ever observed or understood, here, on this small warm world, something has happened that is, by any honest accounting, remarkable. Matter has become curious about itself. Atoms forged in dying stars have assembled themselves into creatures that ask why dying stars forge atoms. The universe has produced, in us, the capacity to look at IC 1101 and feel the weight of it, to sit with 100 trillion stars and try, earnestly and inadequately, to comprehend what that means, to trace the history of a galaxy from its first small mergers in the early universe to the slow evaporation of its final black hole in a darkness beyond any number we can comfortably write down, to do all of this from a distance of more than a billion light-years, using only the ancient light that has traveled to us across that void. That capacity is extraordinary, not because it makes us important in the cosmic sense. We are not. We are brief and small and local in ways that the journey we have just completed makes unmistakably clear. But because it exists at all, because somewhere in the observable universe, matter has organized itself into a form that can experience awe, that can look at something a billion light-years away and feel the appropriate response to its scale, which is not indifference and not despair, but wonder. IC 1101 does not know we have found it. It will shine for billions of years, regardless of whether any mind in the universe ever notices its light. But we have noticed, and in noticing, in measuring, in understanding even partially what we are looking at, we have done something that the universe is not guaranteed to produce. We have made the darkness a little less absolute. We have added to the long, cold history of a cosmos that tends toward disorder, one small and temporary and entirely improbable thing: comprehension. The light from IC 1101 has traveled for more than 1 billion years to reach us. It has crossed a void so vast that the word vast fails immediately upon contact with the actual number. It has arrived at the mirrors of our telescopes, ancient and unchanged, carrying its message from a galaxy that has not been seen in its current form since before complex life existed on this planet. And what that light found, when it finally arrived, was something the universe had been building toward for 13.8 billion years, without any guarantee that it would ever succeed. Something looking back, something wondering, something that, for all its smallness and brevity, is capable of holding 100 trillion stars in its mind and feeling, in the face of that number, not terror, but reverence. The stars of IC 1101 will burn for billions of years yet. The black hole at its center will persist for a span of time that makes the word long meaningless. And long after both of those things are gone, long after every structure in the observable universe has dissolved into the cold equilibrium of heat death, the fact of this moment will remain true. That here, in this brief flowering of complexity between the chaos of the early universe and the silence of the far future, matter became aware of itself and looked out across 1 billion light years of darkness and saw